Okay. We'll start. Online students, can you confirm whether I'm audible? Yes. Okay. Good afternoon, all. So today, as we planned, we'll be starting the new lesson, Archimedes principle. Before that, we finished all questions from the last unit, right? Yes. Okay. So we'll be starting the Archimedes principle, our next lesson. Okay. So first thing, what do you have already heard about Archimedes principle? Anything you know already? I know in O levels you have it, right? I know you have it. In A levels, we'll be starting from there and we are moving towards all advanced questions, right? All the advanced types of questions in Archimedes principle. So today we are starting, right? So what do you know already about Archimedes principle? Online students, you hear me, right? Let me check the audio. Okay, right. So any thoughts? Any thoughts? What do you know about Archimedes principle? About upthrust. Okay, that's one of the keywords we have in Archimedes principle. What about you? Anything you have heard already other than upthrust? Video is stuck. Ini magnetannya nih, ini materi connect nih. Connect. Baru connected lah nih. Dan, am I audible now? Oh. Okay. Then also, and this one here, and this one. Okay. Online students, what about now? What about now? Oh, right. Thank you. Okay, so back to the topic. So what I was asking was what you know about Archimedes principle, right? And I got from expected answer that Amson said the law actually, right? Archimedes principle, right? So first, let's consider a displacement container like this. Look at the board. To get the start, let's consider a displacement container like this. This is called a displacement container, right? This is called a displacement container. This is called a displacement container. Sometimes you might have heard the name already. So we call this displacement container. And let's say the displacement container is filled up to this level. Right? This is an outlet. This is an outlet. And we can fill this only up to the level of the outlet. So otherwise, it will spill out. Right? Now it is filled up to here. Right? Displacement container is filled up to here. And say I have an object here like this. I have an object here like this. And to collect the spill out water, here I am using another beaker. This is a beaker, a normal beaker. Right? Purpose of placing this beaker is to collect this spilling water. Right? Okay, now let's say I'm going to take this all the way down to the liquid. Right? I'm going to take this all the way down to the liquid like this. I'm going to take this all the way down to the liquid like this. Right? This one. If it is taken down, so you know any object takes a space, takes a volume in the space. It is spacious. So it takes a volume in the space. Right? So therefore, once this is taken down, what happens? It acquires some volume from this liquid medium. When it acquires that volume, then the equivalent volume that is equivalent to the volume of this will be spilled out, because initially this water was filled out to the level of the outlet, right? Which means that is fully filled. Now, if I'm inserting another volume, another object with a volume, what happens is that equivalent volume should be spilled out, right? Then we can collect this amount of water here. See? We can collect this amount of water here. We can collect this amount of water here, right? And this is called the displaced volume. It's called the displaced volume. Displaced volume. Because it was displaced due to emerging this, due to drowning this, right? So I immerse this in the liquid, then this. So that is for the displaced volume. That is for the displaced volume, right? Displaced volume. Now, what Archimedes found out was something like this. If the object is inside a liquid, that is sinking in a liquid or drowning in a liquid, he found that there is another force exerts called upthrust. Called upthrust, right? And as the word says, as the name suggests, that is upthrust. That is always working upwards. That is always working upwards. That is an upthrust. Now that thrust force acts here on the object like this. The thrust force acts here on the object like this. And what he found out from this experiment was this thrust is equivalent to, get here, this thrust force is equivalent to the weight of displaced volume. Weight of displaced volume. Weight. Weight is mg. So what he found out was that. Right. So what he found out was thrust is equivalent to the displaced volume, weight of the displaced volume. Right? This is the initial argument he gave. And then we are going to develop this equation in another way, in another format, and get the equation for upthrust. Right? So before moving on to the equation, first we will see what the law is. Right? And then we are going to convert that law into the equation. Right? First, before taking down the equation, take down the diagram. Take down the diagram. Before taking down the equation, take down the diagram. Before taking down the equation, first take down the diagram. Okay. First take down the diagram. And by the way, for this month, the monthly plan is we'll be finishing Archimedes principle with all applications in first 2 weeks, right? And last 2 weeks will be fluid dynamics. It's called Bernoulli's principle. And with that, all mechanics is going to be over. So by the end of this month, we'll finish all mechanics. And when it comes to questions from Archimedes principle and especially from fluid dynamics, Bernoulli's principle, very frequently questions are coming. Very popularly questions are coming, right? Very frequently and very popularly questions are coming. Therefore, just know the month plan and don't miss the month because if you miss even a single class, it's going to affect, right? So when it comes to essay-based questions, essay questions from mechanics, Bernoulli's principle is one of the major parts that you are getting the question, right? So we'll be covering both during this month, right? And the week of the next month will be Unit 3, oscillations and waves, right? Therefore, we'll be finishing entire unit this within this month. So that's the plan. First 2 weeks will be this Archimedes principle, and then for the rest we'll be taking fluid dynamics. Right? Take it out quickly. Finish. Right. So first take a red pen and write down the law. First we'll see what the law is. Then I'll explain what that law means, and we are going to derive an equation using the law. Right. And for all the sum solving, as the equation of thrust, we'll be using that 2D for all the sums coming out. Right. Okay. First, mention the law with the red pen. Mention the law with the red pen. This is Archimedes law, or we call Archimedes principle. Right? Mention the law. When an object is in red, when an object is, read me red pen. When an object is fully or partially immersed. When an object is fully or partially immersed. Fully or partially immersed. I'll mention the keywords here. Fully or partially. These two are one of the two keywords you have to use in Archimedes principle. Now, without these two words, right, you won't be given any mark for the principle. That is how critical, that is how strict that is. Huh? Right? They are the keywords. They are the keywords that is driving Archimedes principle. Therefore, if you are missing keywords, no marks will be given. When it comes to theorems, laws, principles, I have told you these things. Right? When it comes to principles, theorems, and laws, if we miss keywords, no marks will be given. There are no half marks for theorems, for principles, right? Because that is a principle someone has stated already. We can't change the principle. That's the reason. That's the reason. You have to state it with the same words, same keywords as a principle, as a theorem, right? So that's valid everywhere in physics, right? Okay. An object is fully or partially immersed in a static and incompressible static and incompressible fluid. Archimedes principle is not about liquids, not only about liquids. That is not all fluids. But fluid, gas or liquid, right? Any gas or liquid is commonly called a fluid, right? Archimedes principle is not only for liquids. Even though we do most of the experiments for liquids, right? Even if I float a balloon in air, that thrust will be from the gas species, right? So therefore, Archimedes principle is valid for all fluids, right? Fluid. Fluid means liquids plus gases. That's a single word for both, right? Okay, when an object is fully or partially immersed in a static and incompressible fluid, put a comma. Thrust acting on the object. Thrust acting on the object is equal to thrust acting on the object is equal to the weight of displaced fluid. The weight of displaced fluid is equivalent to the weight of displaced fluid. Right? Okay. Now these are the three keywords we have mentioned. Right? These are the three keywords you have mentioned. Please highlight or underline these keywords in your principle. Highlight or underline these keywords. Now, if you miss any of the keywords from these three, right? 0 marks. 0 marks will be given. That is how strict that is. Right? Highlight or underline. Highlight or underline. Okay. Now, before that, what is an incompressible fluid? Incompressible. We define in hydrostatics. At the very beginning of hydrostatics. What is an incompressible fluid? Online students? Online students? What is an incompressible fluid? Oh, incompressible. Just tell me the word incompressible. What does that mean? Compress. We reduce, right? We reduce. Incompressible. What does that mean? Anyone? Online students? Anyone? Correct. Correct. Incompressible means now from this word also we can think of something. Compressible means volume can be reduced. Compressing means reducing volume, right? Compressing means reducing volume. Compressible means volume can be reduced by applying an external force or pressure. Right? If volume can be reduced by applying a force or an external pressure, so when a force is applied, automatically a pressure applies. Because pressure is force of area. When we apply a force on a particular area, it's actually a pressure. Right? Therefore, compressible means volume reduces. Incompressible means volume is constant. Volume is constant. Even if a force is applied, even if a pressure is applied. Right? Such fluids are called incompressible fluids. Right? If you don't know the word, mention this. Incompressible. You better mention this. I'll mention here. Incompressible. 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 We have defined this already in hydrostatics. Right? First day of hydrostatics. Incompressible. And then volume of fluid. Volume of fluid. Volume of fluid cannot be reduced. Volume of fluid cannot be reduced. Volume of fluid cannot be reduced by applying an external force. By applying an external force or external pressure. By applying an external force or external pressure. By applying an external force or external pressure. Right? That is called incompressible. Incompressible. Right? Okay. Now let's see what this principle says. What this principle says. Right? Now, if an object is fully or partially immersed. Now, in this example, I have used a fully immersed object. Right? So even if it is partially immersed, the principle is valid. Right? So if an object is fully or partially immersed, thrust acts on this object. Right? Is equivalent to weight of displaced fluid. Weight of displaced fluid, no? So therefore, if I take that learning from the law, what it says is thrust equals weight of displaced fluid. Equals energy. Right? So we all know that M can be expanded as what? M can be expanded as using density. M is zero. Right? Volume into density. Zero. Then U can be written as M is V rho G. Now tell me, is this rho belongs to the liquid or the object? Is this rho belongs to liquid or the object? Liquid. Any doubts? Online students? Is this rho belongs to liquid or the object? What about this rho? Does it belong to liquid or the object? See from where it derives. Thrust equals weight of displaced fluid. Displaced fluid. Then this mg is the weight of fluid. Fluid is the liquid here. Then this is the weight of the liquid. Then if there is the weight of the liquid, this is mass of the liquid. When mass of the liquid is expanded, this is density of the liquid. And about the volume is also that's the volume of the liquid. But that volume is equivalent to exactly equivalent to the volume of the immersed object. So therefore, For our is we will refer it here onwards as volume of object, but density is for the liquid. Right? Otherwise, if you mistake these two densities with object and liquid, then hereafter the entire sum is going to be wrong. Right? Sometimes both densities will be given. We have to pick the correct one. Right? Okay, now starting from here, the equation derived is Q equals V rho G, where we are going to define all these terms, take down the equation, and we are going to define these terms. We are going to introduce these terms. Right? Start from here, and we have mentioned that from Archimedes principle. From Archimedes principle, and take this down. From Archimedes principle, take this down. I'll ask if you got any questions. Right? If you got any questions, anything to know about? Right? So go on Zoom, you can put your questions to Zoom chat. And the ones who are on YouTube, you can forward your questions to the live chat YouTube. I like this equation, right? This is the only equation we have for plus. This is the only equation we have for plus. Only. Right? Right? Introduce the U, introduce the one by one. U up plus. U up plus. Up plus. V immersed volume. The immersed volume. Immersed volume. Immersed volume. Rho, very important, density of liquid. Density of liquid. Density of liquid. G, gravitational acceleration, flat, resultant acceleration. Gravitational acceleration slash resultant acceleration. Gravitational acceleration slash resultant acceleration. The reason is this: if the liquid is at rest, we only have the gravitational acceleration, or the only acceleration acts on the liquid is gravitational acceleration. In that case, this will be G as gravitational acceleration, just the gravitational acceleration. And if that container is moving or something, we got the same idea in the last class, right? If the liquid container is moving, also HOG changes. When HOG changes, that particular G acceleration changes. So with that, we will do the proof. We will do the proof here. In this proof, HOG part involves. Therefore, with that, the resultant acceleration comes. Therefore, if the container is moving, maybe vertically upwards or downwards, with the acceleration, resultant acceleration comes. Right? Keep that in mind. But when it comes to questions, for more than 90% of questions, we'll only have gravitational acceleration. But rarely, questions are coming from moving containers. When moving container is given, we have to make sure that we are putting the resultant acceleration there, resultant downward acceleration. Clear? Right. As the next point, mention this with a red pen. Mention this with a red pen. Online student, please remind me if I haven't done the recording. You are the one to read. Right? Okay. Mention this in red. So please tell me if the recording is not on, because sometimes when I switch the lesson, sometimes I miss turn on the recording. Right? Forgot to turn on the recording. So if you notice that the recording is not on, because you are the one who is seeing it, because you are seeing it through the screen, right? Physical students don't know. They don't know whether even the online class is going. You don't know. Right? So if you notice that, please remind me. Right? Okay, now it's okay. First point is red. Acting point of acting point of acting point of upper stage. Acting point of upper stage. Acting point of upper stage. Center of buoyancy. Center of buoyancy. You can find the spellings here. Acting point of upper stage. Center of buoyancy. Center of buoyancy. Center of buoyancy. I'll explain this. Right? Second point. Second point. Before that, tell me, what is center of gravity? Center of gravity. Online students? Okay, I need a quick response. Center of gravity. Correct. Correct. Online students? Now, these are from the parts you have already covered. Center of gravity. We covered around 3 months back. 3 months. What is center of gravity? Center of gravity. We only have 3 types of centers in the syllabus. In the whole syllabus, we have 3 types of centers. First one is center of gravity. Right? The point where weight of an object acts. The point where weight of an object acts is called center of gravity. Right? And then center of mass. What is center of mass? We discussed both under center of gravity. Under the main lesson, center of gravity. Center of mass. What is center of mass? Online students? Yes. Good. It's not. What is center of mass? What it reflects is you haven't gone through the past lessons. Right? What is center of mass? We had both definitions of the center of gravity. Center of mass is the point where a force should be applied to move an object without rotating. Right? To move an object without rotating. That is not an acting point. I got one answer. The point where force should be applied to move an object. Yes, exactly. Right? That's the exact answer. Right? Because mass is not acting. Mass is a scale. Only weight acts. Weight is the vector. Right? Mass doesn't act. Mass doesn't act. Center of mass is the point where a force should be applied to move an object without rotating. That is called center of mass. But if the object is symmetric, center of gravity and center of mass are same. If and only if the object is symmetric, center of gravity and center of mass are same. Right? And this is the third center we have, and the last center we have in only. This is called center of buoyancy. Will you explain what center of buoyancy is? Center of buoyancy. Center of buoyancy is the center of gravity of immersed part. Center of buoyancy is the center of gravity of immersed part. Right? As an example, if I consider this kind of an object, look at here. See, now this is partially immersed. Look at the moon. This is partially immersed. So let's assume this is a uniform one and half immersed.
let's say half image. Exactly half image. First tell me where the center of gravity is. If it is a uniform symmetric object, where the center of gravity is symmetric object. At the center, that is where the symmetric lines are going to be intersected. Right? This is the other symmetric line the object has. So center of gravity will be here, G. Center of gravity. Immense volume is, or the immense part of the object is this. The immense part of the object is this. Right? Now, if center of buoyancy is center of gravity of immense part, it should be the center of the immense volume. Therefore, center of buoyancy is at the center of the immense part. We denote it by D, center of buoyancy. Center of buoyancy. Right? If the object is fully immersed only, center of gravity and center of buoyancy will be same. Is that clear? That makes sense, no? If the object is fully immersed, that will be same. Because immersed volume and the total volume of the object will be same. Center of buoyancy is the center of gravity of the immersed part. Clear? But if the object is partially immersed, definitely center of gravity and center of buoyancy are two different points. Definitely two different points. Right? So as a definition, center of buoyancy is now today onwards you have to know all three definitions of all three centers. Right? We only have three centers. Right? I said a physical center centers not in those. Right? To know mechanics only. Right? Center of gravity, center of mass, center of buoyancy. This is the last center of buoyancy. Right? As the next point you must mention in red, keep using red. Center of buoyancy is center of buoyancy is center of buoyancy is center of buoyancy is center of gravity of center of buoyancy is center of gravity of center of buoyancy is center of gravity of immersed part of the object. Immersed part of the object. Check it out. Diagram. Take it down. And clearly mark G and B, center of gravity and center of buoyancy. Right? Okay. Label these two as G, center of gravity, B, center of buoyancy. Label these two. G, center of gravity, B, center of buoyancy. Right. Next heading, find out verification of Archimedes principle. Verification of Archimedes principle. Verification of Archimedes principle. Verification of Archimedes principle. Okay, look at here. Well board. Look at it. I'm going to consider a uniform cuboid that is immersed in this liquid. See, this cuboid is immersed in this liquid. That is immersed in the liquid. Right. Now, when that is immersed in the liquid, if we think of these plane surfaces, how many plane surfaces are here? Red, 2. Yeah, there are 6 plane surfaces. On each plane surface, there will be a force acting due to liquid. Because liquid is going to be in contact with the plane surface. If there is any contact, definitely there should be a reaction, a perpendicular reaction. Right? So therefore, now each and every liquid particle acting on the surface, there are millions of particles here. So infinite number of particles here. Right? Each and every particle acting on the liquid, acting on the surface of the liquid, generates a force, exerts a force on the plane. Right? So therefore, I'm not going to mark all forces. Actually, it's not practical to mark all forces. Right? I'll mark the range like this. Okay? Now, if I consider this surface, right, top surface, the liquid that's from the top, right, weight of the liquid that's from the top, and it is in contact from the top, right. So, what can I say about the direction of reaction on the object? What's the direction of reaction on the object? On the object, liquid that's from the top. Basics. Downwards. Right? Downwards. So it's downwards. And this will be throughout this surface like this. This will be throughout this surface like this. Is it clear? And let's assume the resultant of all these forces acting on the top surface as a resultant. There will be infinite number of forces acting from here to here along the top surface. Right? So let's say the resultant is F1. So I'm considering this resultant force as F1. Resultant. Clear? Now think of the bottom surface. Think of the bottom surface. It's like this. This is the bottom surface. Now the liquid is in contact from the bottom of the bottom surface, like this. Right? Think of the contact and tell me what's the direction of reaction force on the bottom surface. Right? The contact is from bottom. Contact of the liquid is from bottom, of course. Right? Basic force marking. Therefore, here there will be infinite number of forces which are acting upwards throughout the bottom surface, like this. And I'm going to consider the resultant of all these forces as F2. Resultant of all these forces as F2. Right? Okay. Now, what about these surfaces? First, let's see the electron. This surface, this one here. Liquid is in contact from the left. From the left. The reaction force is rightwards. Right? Reaction force is rightwards. Think of the natural direction of these forces. Huh? So like this. They are rightwards. They are rightwards. Right? And what about here? Liquid is in contact from the right side and the force is towards left. Right? Force is towards left. So I'll be marking it here. I'll be marking it here. Right. There will be forces on this surface here and the surface behind as well. But I'm not going to mark them because these two forces are going to be, we'll imagine that the other two forces are going to be inward and outward forces as cross and dot forces. Inward and outward forces. Right? So therefore, without marking these two, we will imagine what happens. First, take this down. Take down the diagram clearly, and if you are using different colors, use different colors for these vertical and horizontal forces, because we are going to go into some depth about these forces for this verification. Right? So you have to have a clear diagram. For a clear diagram, if you are using different colors, you can use any different colors. And let's label the resultants of these two as R1 and R2. Resultant of the horizontal force here, let's say R1, and the resultant leftward horizontal force R2. Label all. Label all. Meanwhile, you can ask any question if you have anything. If you have anything to clarify. Online students, if you have anything, you can ask. Okay, please. Okay, let's assume height of this object as h. Let's assume this height as h. Right? Height of the object as h. And height from top surface to liquid surface to the top surface of the object, let's say h1, and height from top surface to bottom surface of the liquid of the object, let's say h2. Let's say h2. Right? Okay. Now, with your knowledge on center of gravity and resultant forces, right? Tell me, what will be the acting point of R1 and R2? What's the acting point of R1 here at this surface and R2 here at this surface? What can you say about that acting point of the force? Resultant force. R1 and R2, both are resultant. What can we say about the acting point? Is it simply, this is what I'm asking, is it at the center of this side, or is it close to bottom, or is close to top? What can we say? Center. Center. Online students? Yeah, that is center. That is center. Because the reason is the resultant of these forces be at the center, right? Be at the center. And Now, if I say the height from here to here as x, this is also same. There is also x, right? Now, if I think of these two forces, R1 and R2, if I think of these two forces, what's the relationship between force and pressure? Force and pressure, right? If this here pressure is force over area, so force can be written as pressure times area, right? Now, if this is open to surroundings, we have atmospheric pressure here at this surface. If there is open to surroundings, if you need to write pressure at this point, it should be what? Let's assume density of this liquid as rho. What is the pressure at this point? If there is x distance below the surface, P naught plus x rho, right? Pressure at this point is also P naught plus x rho, which means these two forces are going to be equal. Is that clear? Right? I'm not going to write the force, they are going to be equal. Areas are also equal, that's a cuboid. That's a cuboid. Therefore, if the height is same, pressure will be same. If pressure is same, force is same. Right? So if you need to write this down, this is how it comes. Okay? Look at the board. R1 can be written as pressure acting at this point is P naught plus x rho g going downwards through a liquid plus h rho g. Now x is the vertical height of the liquid from surface to this point, right? A. So let's assume this area is A. And about R2, that's also very much similar. R2 is P naught plus x rho g, same A, right? From this we can see, therefore, R1 equals R2. If R1 equals R2, what can you say about the horizontal resultant force? Horizontal resultant force cancel each other. So horizontal resultant is null, it's zero. It's zero, right? Therefore, horizontal resultant acting on this object is zero because these two horizontal forces are going to be right. First, right up here, pick it. Stay down up to here. Right down. Below this answer with the red pen. The red pen. Measure this. Therefore, horizontal resultant force acting on. Therefore, horizontal resultant force acting on. Therefore, horizontal resultant force acting on object becomes zero. Acting on object becomes zero. Acting on object becomes zero. Right? Within brackets, F horizontal is zero. Right? F horizontal is zero. Right. Now, if I use a similar approach to determine vertical forces F1 and F2, vertical resultant forces F1 and F2, see, we can write F1 and F2 again using the same equation. P equals pressure into area, and for F1, you can write what's the pressure acting on this top surface. P naught plus H1 rho g, right? P naught plus vertical height from top surface to liquid surface. Liquid surface to top surface of the object is H1. That is H1 rho g. Right? Let's assume this area as A. Let's assume this area as A. Right? for F2, what's the pressure? Acting at F2. Bottom surface. P0 plus. I consider this as H2, then there is H2 rho G times A. Right? These two forces are different. These two forces are different. And tell me which force is greater from F1 and F2. Which force is greater from F1 and F2? Look at the board and listen very carefully because this is the verification of Archimedes principle. And if you understood this, then it is not going to be a magic how this upwards force acts. Right? You can do the applications even without knowing the verification. Right? Like machines. Be like machines. Understand the concept. Right? Difficult concept. F2. What's the reason? What's the reason? One line students? Simply, higher the vertical height, higher the pressure. Higher the vertical height, higher the pressure. Higher pressure means higher force. If 2 is greater, right? Then for sure we can say F2 is greater than F1. For sure we can say F2 is greater than F1. If F2 is greater than F1, tell me in which direction the vertical resultant force acting on the object is going to be. In which direction? Upwards or downwards? Upwards. Upwards. Which means since F2 greater than F1, an upward resultant force remains on the object. An upward resultant force remains on the object. That is called the upthrust force. That is called the upthrust force. So upthrust is totally due to what? Pressure difference. Pressure difference. Forces due to pressure difference. Right? Thrust is due to pressure difference. So this is how it acts. We will prove this. Now come up to here for the vertical forces. Right up to here. F2 greater than F1. And identify that F2 is greater than F1. You should be able to argue on these things as physics student. You by heart and if you parrot Archimedes principle and the equation, right? Still you can do majority of questions. But when there's a question is that with the new thinking, definitely will start. That's the thing. Don't be like machines. Always understand the concept. If you got the concept, this is something applicable throughout physics. And combine maths as well. If you got the concept, you will do any type of question. Otherwise, you will do just the typical question, the ordinary question that everyone do. That everyone does, right? Otherwise, if a question came up with a new thinking, you will be stuck. So always understand the concept, right? Concept is the key here. So I have told you in physics, it's around 90% of concepts, right? Okay, now determine this vertical resultant. Vertical resultant, let's say FP. Let me erase this from here. So vertical resultant FP, right? FP is F2 minus F1, F2 minus F1. And answers of F2 and F1 are here, right? Answers of F2 and F1 are here. F2 is E0 plus H2 rho G times A minus F1 is E0 plus H1 rho G times A. Right? A is common. A is common. So I'm going to take A out. If A is out, P0 plus H2 rho G. And if A is out, minus P0 here, simplify the bracket, minus H1 rho G. Minus H1 rho G. Right? See, P0 to P0 cancels. P0 to P0 cancels. And this vertical resultant remains as from here you have A and here H2 rho G minus H1 rho G. Rho G is also common now. Rho G is also common. Right? Rho G is also common. take it out. Then A times here H2 minus H1 times rho G. A times H2 minus H1 times rho. Right? What is H2 minus H1 from the diagram? What is H2 minus H1 from the diagram? Height of the object. There is H. I consider it as H. H2 minus H1 is H. Right? Height of the object. Then we can replace this with H. We can replace this with H. Here, then vertical resultant is A into H rho G. A into H rho G. I'll write the rest here. So you can do it on the end H. Right? I'll write the rest here. Right? What is A into H? What is A into H? Cross-sectional area into height. What is A into H? That's a volume. That's a volume. Right? A times H is the volume. Volume of object. A times H is the volume of object. Right? There's nothing you can. Then, if I consider the volume of object as V, how I can replace this AH with V? That is the volume of object. Which means, vertical resultant equals V rho G, and this vertical resultant is defined as upwards. This vertical resultant is defined as, right? This is called upwards. This is what is defined as upwards by Archimedes. Now, you equal V rho G powers. So this is how he proved the equation. This is what the experiment was, right? And then this is how the verification is done. This is how the verification is done. Now you can clearly see this G comes from HO. This G comes from HO. That's why I say if the liquid container is moving, HO changes. Then resultant acceleration should be put. Then accordingly, the acceleration changes here. Right? U equals V rho G can only if the surrounding liquid is at rest. If there is not at rest, the resultant acceleration will be used. Because when an object is, when a container is moving, right? The last part we discussed last day, when a container is moving, right? HOG changes. G in HOG changes. When it changes, it impacts V rho G. That is why, that is how the resultant acceleration comes. That is how the resultant acceleration comes. This is the verification of Archimedes principle. And this is questionable. This is questionable. You will be getting questions to prove this. Right? You are getting questions to prove this. Then you have to know this proof. You have to know this proof, how to prove. Right? Starting from the diagram, you will be able to prove all the way up to here. Right? Not a very frequent type, not a very popular type, but there are questions from the proof of the Archimedes principle as well. Right? So this resultant force, this vertical resultant force, was defined as. So therefore, first is not going to be a magic force that is coming out of nowhere. It is coming from the resultant of these forces. Horizontal resultants can cancel each other. And about these two surfaces also, it will be the same as these two surfaces. It cancels it. Because about the front and the behind surface, height will be same. So the resultant point, they cancel each other. So that's why I even didn't mark it. Right? And only unbalanced forces will be from F2 and F1. Only unbalanced forces will be from F2 and F1. And those two unbalanced forces working together and contributes exerting this upward. So that vertical resultant is called upward. That is very important. Because from that, you will be getting a type of question in the coming up parts. Right? To determine reactions. Right? That's a type of question. Without marking up thrust and by marking these separate reactions, we can obtain these reactions. Now, while you are obtaining the reactions on surfaces, if you mark up thrust, that will be duplicated. That will be duplicated. That's the thing. Therefore, clearly you have to know the upthrust is the resultant of vertical forces. Otherwise, if these vertical forces, if you mark upthrust again, both forces are duplicated. Right? So that is why this is very important. Starting from here, right? Starting from here, prove up this point. And you can ask questions if you have anything. You can ask question if you have anything. The clarification needed, clarifications needed, you can ask. Sir, can you repeat that point? What's the point you were asking about? Sorry, I missed that. Yeah, what's the point you were asking about? Therefore, horizontal result. Previous point. Therefore, horizontal resultant acting on object becomes zero. Therefore, horizontal resultant acting on object becomes zero. Please mention this point with the red pen. Put an asterisk mark and mention here. Put an asterisk mark and mention here. The resultant force of the resultant force of the resultant force of the resultant force of vertical forces. The resultant force of vertical forces acting on the object. Resultant force of vertical forces acting on the object is called is called upthrust force. Is called upthrust force. Is called upthrust force. No contribution from horizontal forces, right? Because they cancel each other. All four horizontal forces on horizontal surfaces cancel each other, and only remaining unbalanced force in the system is vertical, right? So that is why thrust is actually an upthrust. That is why it's acting upwards, right? It comes from F2 and only from F2 and right? Okay. Now, if you are asked to prove this, if you prove just by marking vertical forces, that's enough, right? This is for your reference that I showed you the horizontal forces are zero, right? Otherwise, if this was question, marking vertical forces for the proof is enough, right? Okay. Any questions up to here? Any questions up to here? No. Good. Online students. Online students. Any questions up to here? If it's clear, just say it's clear. Or at least put a reaction, a thumbs up or something. Is it clear? Yeah. Okay, good. Okay, we are moving on. We are moving on. Next heading, write down law of flotation. 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 Finally, what is law of flotation? That's also in order. In order. Just thoughts. Any idea about law of flotation? Both laws are in O levels as well, but you don't know. You don't have any sounds and implications, right? Okay. If they have any, they are just to find the upthrust and all that. Right. Law of flotation is this. Okay. Actually, law of flotation is derived from Archimedes principle, but that's a different law. Right? If law of flotation is asked, don't write Archimedes principle. Sometimes they are asked well, even if the law of flotation is asked, they are writing Archimedes. They are two different principles, two different laws. Right? And this is derived from Archimedes principle. That is true. And the law of flotation is only driven from Archimedes principle. But that is a different law. What is floating? What does that mean by floating? Floating and object. Floating. Floating means if any object is not moving downwards or upwards in a liquid, if that is at rest on the liquid, inside a liquid, or maybe at the surface of the liquid, that's called floating. Right? Floating can happen even if the object is fully or partially immersed. Right? Even if the object is fully immersed, that's also floating. If there is at rest at a particular point, that's a floating. Right? So if the object is inside a liquid or at the surface of the liquid at rest, that's a floating. Floating. Right? So it cannot be drawn. Right? If there is drawing, that is not a floating. Right? This is law of flotation, and that is only valid for floating objects. And when it comes to Archimedes principle, know the difference. When it comes to Archimedes principle is valid for any kind of an immense object. Float තුනක් අවුලක් නැහැ, float නැති වුණත් අවුලක් නැහැ. අපි අතින් අල්ලගෙන ඒක immerse කරලා තිබ්බත් අවුලක් නැහැ. Floating means that is something that happens naturally. Floating is always natural. Naturally, it is flowing without having any external intervention of other forces. Right? That is what is meant by floating here in law of flotation. අතින් අල්ලලා මම තියාගෙන ඉන්න object that is not a floating. ඒතර අපි external involved වෙලා එහෙම වෙයි. Naturally it should float. That is called floating. Right? So when it comes to law of flotation, this is what it says. First listen. Don't write anything, just listen. Right? If an object floats on a liquid, right? And here also there are keywords there. Now, if you didn't mention your keywords, it's same as Archimedes principle, no marks will be given. Simple as that. Right? Keywords are the fluid should be static and incompressible. Right? Fluid should be static and incompressible. Right? So what law of flotation says is this: if an object floats in an incompressible and a static liquid, upthrust acts on the object is equal to, there are two parts. See, upthrust acts on the object is equal to mg, and center of gravity and center of buoyancy will be on the same line, same acting line, right? Look at here. Look at here. Before writing, first let's see how this comes. First, let's see how this comes. Let's say this object floats on this liquid like this. This object floats on the liquid like this, right? And this is the immersed part. This is the immersed part, immersed volume. And center of gravity is somewhere at the middle here. Let's say this is center of gravity, and from center of gravity, weight of the object acts on. Even if it floats, weight of the object acts, right? And center of buoyancy is the center of gravity of the immersed part. Let's say here, from center of buoyancy, which force acts? Center of buoyancy, which force acts? Upthrust, right? Then from center of buoyancy, upthrust acts like this, right? Now, if this object is at rest without drowning, right? Without drowning, without sinking, drowning means sinking. If this object is at rest without sinking, it should be adhering to a vertical equilibrium. It should be following a vertical equilibrium. Then vertical equilibrium means U equals mg. So that is how the first part of law of flow diagram comes. U equals mg. No any external forces. On weight with the upthrust. That is called flow. Right? Now, if I keep this by applying a force, still it will float. But that is not explained here in law of flow diagram. We can solve all these questions, but in law of flow diagram, there is only about natural flow. When it comes to questions, even if external forces are given, without using law of flow diagram, by using vertical equilibrium or any other things you know from Newton's laws and the other things, we can solve the question. But we can't use law of flow diagram. Law of flow diagram is just for natural flow, right? And the other thing is, now center of buoyancy is here, center of gravity is here. If these two are two different points, right? Let's say we are here. Let's say center of gravity is here and center of buoyancy of the object is here. Two different points. Two different points. Now what's going to happen is, with these two, there will be a force couple that rotates the object. Because you know, U and mg are equal. So vertical equilibrium, U and mg are equal. Then it creates a force moment. Since there is a force moment due to an equal pair, that's a force couple. Then in that force couple, it rotates. There is rotating, it is not at rest. Resting means should rest even without a rotation. Even without a rotation. Right? Therefore, to omit that rotation, to omit that force moment, definitely these two should be acting on the same line. When they are acting on the same line, there is no perpendicular distance, so no force moment. Since there is no force moment, no force couple, no rotation. That is at rest. Right? So that is how the second condition of flow of flow diagram comes. Right? Otherwise, if these two are going to be two different points, this will rotate and it will make unstable inside the liquid. Right? මොන මේ කළා බලන්න පුළුවන්. කළා බලනවා කියන්නේ මෙහෙමයි. අපි මේ පැත්තට පොඩ්ඩක් weight එකක් වගේ add කරොත් එහෙම center of gravity එක මේ පැත්තට ගන්න පුළුවන්. මොකද center of gravity නේ. අපි ඒකට අදාළ ඉවරනේ. මේ පැත්තට weight එකක් තියෙනවා. දැන් weight එකක් තිබුණා center of gravity මේ පැත්තට එනවා. මේ shift එක එනවානේ. force moment එකක් මේ පැත්තට කරගෙන. කරලා පෙරලා. Okay? Right? So that is why the second condition is center of gravity and center of buoyancy has to be acting on the same vertical line. That is on the same vertical line only, it will be resting without any linear motion or rotation. Right? If there is resting, there should be a linear motion and a rotational motion, any kind of a motion. It is resting. Right? So that is how these two conditions come. Right? First take this down. Diagram. Only the diagram. Only the diagram. And you can ask if you have any questions. You can ask if you have any questions. Okay. Write down law of flotation. You read. Okay. Write down law of flotation. Write down law of flotation. When an object is floating in a when an object is floating in a static incompressible fluid incompressible fluid put a comma and write down these conditions separately. Condition 1 from number 1 and write down, right? When you are writing the law, it is okay to write it as a law in a single line. That is fine. This is for your reference, easy reference. When you have these two conditions, you can easily see two conditions. Then you can easily study. That's why I'm writing separately. Otherwise, it's not a must. Right? Put a comma and condition 1. Write in words. Upthrust equals. Write in words. Upthrust equals. Upthrust equals to weight of the object. Upthrust equals to weight of the object. Upthrust equals to weight of the object. Weight of the object. Right? Within brackets, write this down. U equals anything. Within brackets, U equals anything. When you are writing a law, we have to write everything in words. Right? In a law, you have to write everything in words. Don't use symbols, just symbols for the law now. Here, in brackets, I'm writing U equals mg. But if you just write U equals mg, okay? Right? Because the law should be self-interactive. If I write U and mg, right? Who knows what U is? That's the thing. Who knows what U is? Right? It should be self-interactive. Always you have to use words, exact words. And once the term is introduced, then you can use the terms it needed. Right? Then condition 2, from number 2, and center of gravity and center of buoyancy. Center of gravity and center of buoyancy. Center of gravity and center of buoyancy. Center of gravity and center of buoyancy are on the same vertical line. Center of gravity and center of buoyancy are on the same vertical line. Are on the same vertical line. Are on the same vertical line. Right? And highlight same vertical line. Highlight to underline. Highlight to underline same vertical line. Highlight to underline same vertical line. Same vertical line. Same vertical line. Look at it. put this as a node, and take this down again. Take this diagram down. And by considering, this is how this derives. By considering vertical equilibrium. By considering vertical equilibrium, we can say vertically upward forces equals vertically downward forces. Vertically upwards forces equals vertically downward forces. Vertically upwards U, vertically downwards mg. So this is how U equals mg cos. This is how U equals mg cos. You get it? Take it down as a node. Take it down as a node. Hold your questions if you have anything to know, if you need to clarify anything regarding the parts we discussed from the beginning, right? Hold your questions. Good. If any object floats, always it will be in a vertical equilibrium. Always it will be in a vertical equilibrium. Because if it is not in a vertical equilibrium, there will be an external unbalanced force remaining in the system. Then that force will drag this either downwards or upwards. That depends on the density. If this density is less than the density of liquid, right, it's coming upwards. If we release it inside the liquid, if its density is greater than the liquid of the liquid here, it goes downwards on the release. And it's drawn, sinks. Right? Any questions up to here? Online students, any questions up to this point? We discussed two things. First one, and the main principle here is Archimedes principle, right? And second one here is law of flotation. So this is why I told you law of flotation is derived from Archimedes principle, because U involves that derives from Archimedes principle, but there are two different laws. Archimedes principle, and with that principle, this law is derived. Right? So these two will be the two main paths we have to solve sums, to tackle questions. So anything to clarify up to this point from the beginning? Anything? If they ask nothing, just say it's clear. If they ask nothing, you can say it's clear, or at least put a thumbs up. Simply, the symmetric object center of gravity is where the intersection lines are intersect. Right? There is an asymmetric object in reverse. Right? There are different techniques, different methods to determine the center of gravity. Right? But since there is symmetric, these are two symmetric lines. The point where these two symmetric lines are intersected is the center of gravity. The center of gravity is point where the rate of the object acts. And center of gravity is the point where center of gravity of the center gravity of the given solution. Given solution is far. And the solution is also limited. Center of the given solution that is center of fluid. Center of fluid. Right? Fluid means floating. Floating. Buoyancy means the meaning is like floating, buoyant. Buoyant, buoyancy. Buoyant means the meaning is very similar to floating. Oh, all good. Right. Okay. Now we are moving on to first type of questions. So this is the initial theory part you need to know to do first type of questions. This is the initial theory part, right? Initial theory part is this is the main theory part you have in Archimedes principle, and the coming up parts are actually derived from these things. These two are the main two theory parts we have, right? In two theory parts we have. Let's try out some questions and see, right? Okay, take this down. Question one. Take this down. Question one. Take this down. Write down. An object floats. An object floats. An object floats. Half immersed. An object floats. Half immersed. Half immersed in a liquid of. Half immersed in a liquid of density rho. In a liquid of density rho. If cross-sectional area, if cross-sectional area of object is capital A, if cross-sectional area of object is capital A, and if cross-sectional area of object is capital A, and height is simple h, height is simple h. Determine weight of the object. Determine weight of the object. Determine weight of the object. This diagram is given. Take this down. This diagram is given. Take this down. Okay. So weight of the object is asked, right? Now, in the question it says it floats, right? It floats. If it floats, it should be a vertical equilibrium, right? Always get used to write vertical equilibrium from here onwards, because the thing is, in the coming up parts, these are the simple questions. Yeah, starting from simple questions, but in the coming up parts, you will get questions with not just U and mg, with other forces as well. Then we have to consider all other forces if there are more forces, right? Therefore, always get used to vertical equilibrium. Right? To get vertical equilibrium, we need to check for all vertical forces acting here. Right? Then mark all vertical forces. From center of buoyancy, upthrust acts, and from center of gravity, mg acts. And we are to determine mg. Let me mark it as W, because no need to mark it as mg. We are just to determine it. It's a W for my ease. That is W. and center of buoyancy is here, center of gravity is here. That is not mandatory to label these two. This is just for your reference, right? Mark all forces. Mark all forces. Now, if all vertical forces are marked, you can consider vertical equilibrium. Mention it and consider vertical equilibrium. Okay. I'm explaining this since in the first question by considering. So I'll be letting you to do next question onwards, right? By considering vertical equilibrium. Vertically upwards forces equals vertically downwards forces. Vertically upwards I have U. Vertically downwards W. Right? Vertically downwards W. And now U is not given. Instead, rho of the liquid is given and some dimensions of the object is given. Right? Okay. Then we can expand U. What's the expansion of U? We have only one expansion for U. U is 0. U is 0. Right? Only one expansion. U is 0. Expand it. V. Did I give you the inverse, right? Now, within brackets, write down. Within brackets, write down. Within brackets, write down. Did I say half immersed? So that's what I asked. Okay, it's half immersed. Then, since there is half immersed, H over 2 height is immersed. Right? U is 0 G equals W. And V can be expanded as what? Volume is cross-sectional area into height. And immersed height here is H over 2. Then this is A times H over 2 rho G equals W. I asked weight, right? Okay. So weight equals, simplify this if it is simplifying, H rho G over 2. H rho G over 2. Right? I gave you a question which came to my mind. So that's why I asked you, I gave the immersed height to what? So since that is given as half immersed, right? Since that is given as half immersed, you can write the immersed volume like A times H over 2. A times H over 2. This is the immersed volume. Immersed volume. Done. 3. Others? Connections? Usually it should be within July. On this school, that's how it is. It's within July. So I have informed about the Valentine's Day. Other students, announcements. Noted. Noted. Online students. Okay, finish. Finish. Okay. Any questions from this before we go to the next one? Because next question onwards, I'll be letting you to tackle the question. I'll give you some time and then I'll start the question. Right? So, do you need me to explain another question or can you handle alone? Handle alone. Very good. Handle alone. Online students? Online students? Handle alone. Very good. So likewise, you should be able to take challenges, accept challenges. Right? That confidence in you. Right? You are confident that you can handle alone. That's very good. Right? That's actually a good attitude you have to have when you are moving along the line of the life. Right? We have to accept challenges. Right? Always it's not going to work the same way you expected it to be. Right? Definitely we will face challenges. In those cases, in such cases, we have to accept challenges. Right? Accept challenges and face challenges. Right? Simply, you should be able to challenge the challenge. That is how we are dealing with challenges. Maka challenge के लिए अभी give up करना ना और हमारा challenges give up मतलब कितने का कौन succeed right challenges के लिए क्या है इन्हें के challenge करना होगा what we hear is challenge करना even A levels is a challenge. That's the biggest challenge you have in this stage of life, right? And once you are moving on, right, after A levels, higher studies, jobs, corporate fields, and everything, then you will get more challenges. Then we will have A levels. And then A levels, right? For now, the biggest challenge you have in front of you is A levels, right? But when we are moving on to the real life of A levels, real society, real life of A levels, we'll be facing more challenges. We want to shape up when we get into running our team, right? What's around? Some of the not accept challenges, right? It comes to us, right? Once it comes, we have to accept it, face it. And we have to do something to eliminate that challenge. We have to do something to deal with the challenge. Right? That's a skill you should do. Right? So that's attitude is very good. Right? That you are confident that you can do all. Very good. Next one. Question 2. Question 2. Question 2. First write down. First write down. A cube of side length A. A cube of side length A. A cube of side length A is immersed in two liquids. Is immersed in two liquids as immersed in two liquids as as equal volumes inside each, as equal volumes inside each, as equal volumes inside each. As equal volumes inside each. Right? If densities of liquids are rho 1 and rho 2, if densities of liquids are, if densities of liquids are, if densities of liquids are, if densities of liquids are rho 1 and rho 2, if densities of liquids are rho 1 and rho 2, right? Question 1, part 1, problem 1, part 1. Determine total upthrust. Determine total upthrust. That is also called net upthrust, right? Total upthrust or net upthrust. Determine total upthrust at an object. Determine total upthrust at an object. Part 2. Determine mass of the object. 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 Okay. Take this down. This diagram is given. Take it down. This diagram is given. Take down the diagram. Take down the diagram. Right? Okay. Do you need me to explain or you're going to start? One cube, two different liquids, two different visible liquids. මේ liquid layer එක මැද්ද මෙයාට commercial එකක් මොනවද? මේ තියෙන එක තේරුම් නැද්ද? මේ තියෙන එක තේරුම් නැද්ද? මේ තියෙන එක liquid එක. Rho 1, right, is a bottom liquid. Rho 2 is the top liquid, and in between both this floats, the object floats, right? Liquids දෙකකින්ම යාම දෙකක float කරනවා. ඒක float කරනවා මේ line එක ගන්න. This is separation line. It floats in two liquids at the same time, two liquids. Two visible liquids like this. Okay, try. No, before trying, tell me one thing. This is the only question I'm asking. Tell me one thing, right? How many upthrust forces act here? How many upthrust forces act here on this object? No upthrust. 1, 2, 3, 4. MCQs. 5 answers. 1, 2. Online students, quickly respond. 2. What about YouTube? Zoom. I got 2. It's 2. The reason is thrust is zero G. When density changes, it cannot be a single upthrust because when density changes, the upthrust changes. Then this part is, look at here, this part is immersed inside the liquid of density rho 2, right? Above half, top half is immersed inside the liquid of density rho 2, right? So with that, from center of buoyancy of that part, that upthrust acts. So let's say there is U2 corresponding to rho 2, right? And this part of the object is immersed. This part of the object, see, this part of the object is immersed inside the liquid of rho 1, right? The liquid of rho 1, center of buoyancy is somewhere here, and from that point, U1 acts. U equals 0 G now. Rho dekha ke value make කරන්නේ මොකටද දෙකක් use කරන්නේ U equals 0 G නේ. එතකොට ඒක ඇතුලේ rho 1 plus rho 2 කියලා දාන්න බෑ නේද? හරි. ඒ rho දෙකක් තියෙනවා නම් U එක දෙපාරක් කියන්න වෙනවා. Is it clear? Now, in U equals 0 G, you clear on that V is the immersed volume, right? Then for U2, the corresponding immersed volume is the first half, top half, and for U1, the corresponding immersed volume is the bottom half. Is that clear? Liquid තුනක් තිබ්බොත් තුනක් වෙනවා. තුනකම මෙයා immersed වෙලා ඉන්නවා. හරි? immersed වෙලා ඉන්න liquids ගන්නට ඔයාලට අප්‍රස් focus එනවා. immersed වෙලා ඉන්න liquids ගන්නට අප්‍රස් focus එනවා. Is clear? Okay. Right now. I'll give you 2 minutes. By that now, 2 minutes. Quickly. Finish both parts. We'll discuss in a minute. Finish both. Correct. Okay, let's start. I'll start. Total upthrust is first part. Total upthrust is U1 plus U2. Right? Total upthrust is U1 plus U2. Right? I'll denote this as UP. Total upthrust. UP. Right? U1 plus U2 mention these external equations separately. U equals 0, G. Always you have to mention separate equations, external equations separately. So question. Total of plus, yeah, good. And V should be substituted. V is not given. V is not given. Who is that? Either. V is not given, right? So you can't keep any answer with not given terms, right? Okay. U equals U1 plus U2, and U can be expanded as V also, right? Then let's say this is V1 rho 1 G, and this is V2 rho 2 G. And I said equal volumes are equals in each liquid, right? And that's a cube volume. No, cube. That's a cube. That's a cube. Then total volume of the cube is a cube. A to the power 3. Right? Then half of the volume is a to the power 3 over 2. A cube over 2. Right? So we can write this volume as a cube over 2. Length into breadth into depth. A cube over 2. Rho 1 G plus this is also same as a cube over 2. Rho 2 G. A cube G over 2 is common. So 1 plus 4. This is the total of the sets. A cube G over 2. Yeah, that is correct. That is correct. Right? Second one. Mass, right? If you need mass of the object, make sure you have marked on vertical forces because we are going to consider vertical equilibrium. Right? If you are considering vertical equilibrium in your diagram also, the considered forces should be marked. And effects from center of gravity, let's say mg. Center of gravity is here. Consider vertical equilibrium by considering vertical equilibrium. Vertically upwards forces equals vertically downwards forces. Vertically upwards you have two forces now, U1 plus U2. U1 plus U2. Vertically downwards only mg. Right? We know the final answer of U1 plus U2 because total upwards is UT. You can take this value. You can take value and plug it. U1 plus U2 is known, that is UT. U total is mg. So UT is a cube G over 2 rho 1 plus rho 2 mg. We need m. G to G cancels. G to G cancels. So mass is a cube rho 1 plus rho 2 over 2. A cube rho 1 plus rho 2 over 2. Right? Make corrections if you have any. Good. Any questions? Any questions on this? Finish? Any questions? Quickly. Online students? Any questions from you? Okay. Mention this after the question with the red pen. Mention this after the question with the red pen. Mark upthrust forces. Mark upthrust forces. Mark upthrust forces. Mark upthrust forces from each liquid. From each liquid. Mark upthrust forces from each liquid separately. Mark upthrust forces from each liquid separately. Mark upthrust forces from each liquid separately. Right? That's it. Okay. Question 3. Question 3. Write down. Write down. A solid sphere. A solid sphere. A solid sphere of radius r. The solid sphere of radius r and density rho naught. Radius r and density rho naught. The solid sphere of radius r and density rho naught floats in a liquid. Floats in a liquid as shown. Floats in a liquid as shown. Floats in a liquid as shown. Determine. Determine. Determine density of liquid. Determine density of liquid. Determine density of liquid. This is the given diagram. Question 3. Okay, start working on the question. Start it. What's the density of the sphere? Rho naught. Again. Rho naught. You heard the question, right? Didn't you? I'll start in 2 minutes. And all of you there in the graph section, right? Graph coding. All of you there, right? Maxwell. Maxwell. All of you there, right? Yes. What about the others? Others? Yes. Wait, no one says no, which means all of you are there. Right. Once I give you graphing questions, right, then you should be able to do. So generally, I think then questions do not say and if anyone of you were not there, please go through that part because once you are getting graphing questions, then I'll be also giving graphing questions, right? I'm not going to explain about plotting graphs to that depth. Graph theory theory explain that day you got around 20 graphs, around 20 graphs. अभी इससे डिस्कस करा है. And graphing is not something you can by heart or you can parrot, right? Accordingly, for what is given, you have to model with an equation and take it to one of these standard formats or do other things, and you have to plot the graph instantly for that point, right? Graph එක මතක තියාගෙන යන්න බෑ reaction පුළුවන් graph එකේ shape එක වෙනස් වෙනවා. අපි දැන් discuss කරන්නේ එකම equation එක graph සමහර වෙලාව මම හතරක් පහක් හයක් යන්න axis වෙනස් කරලා ඉතින් equation එක දැනගෙන ඉන්නට වැඩක් නැහැ. Axis වෙනස් කරගන්න graph එකේ shape එක වෙනස්. Right? Finish. Okay. Let's start. What did I do? Sorry? I asked Ronnie. Ronald. See? Okay. Now, if it floats, again, we are going to consider vertical equilibrium. We don't have any other option. We have only one thing for vertical equilibrium. To consider vertical equilibrium, mark up thrust, and mg. Now, since the total volume of the object is enormous, center of motion and center of gravity in this case are same. That is in this case, that's it. Fine. Now consider vertical equilibrium. Consider vertical equilibrium. Vertically upwards, force equals vertical downward force. Vertical upwards, I have u, downwards mg. Right? U can be expanded as v rho g. U can be expanded as v rho g equals mg. Right? G cancels. Okay. Now, these are sphere. If radius is r, volume of the sphere can be written as 4 3 pi r cube, right? Volume of the sphere can be written as 4 3 pi r cube. Then this V is 4 over 3 pi r cube, and density of the liquid is to be determined. So I consider it as rho, let's say rho, and m. This m can be expanded as, now this is mass of what? This is mass of object, sphere, right? The mass of object can be expanded as V rho, V of object times rho of object, right? So don't mess up with two rows of liquid and rho of object. Because they are clear, like right? Mass of object can be written as V of object times rho of object, right? Then mass of object is V of object, no? That is same. V of object is also that is sphere. 4 3 pi r cube. Now inverse volume and volume of the object is same, right? 4 3 pi r cube, and rho is rho. Oh, it is given wrong, right? Cancelling terms. Cancel all cancelling terms. 4 3 to 4 3 cancels. 5 to 5 cancels. R cube to R cube cancels. Rho equals rho no. Rho equals rho no. Rho equals rho no. This happens always. This happens always if an object floats inside a liquid as fully released. මාරේ ඕන ඔබ්ජෙක්ට් එකකට fully immersed වෙලා එයාට float වෙන්න පුළුවන්. Floating කියලා කියන්නේ surface එකේ විතරක් වෙන එකක් නෙමෙයි. ඇතුළේ float වෙනවා. Even inside the liquid, if it is at rest, that's floating. Right? So this is such a scenario. This is such a scenario. Right? So just keep in mind that this is only valid for solid objects. Huh? If you have a solid object which is a fully immersed, as the volume of the object is equal to the immersed volume, always densities are going to be equal. Right? That is always happening. That is always happening. Right? Take a question. Take it out. Now, if you didn't do before, take it down. Yeah, one says no. Yeah, it's correct. Correct. And next Thursday, listen. Both online and physical students, listen. And about next Thursday is a burden, right? And next Thursday is a void day, right? So what do you want me to do? Do you holiday or doing the class as usual? Online students? Yeah, online students. Question, right. This is the red pen question. If an object floats, fully immersed inside a liquid. If an object floats fully immersed. If an object floats fully immersed inside a liquid, density of liquid equals density of object. Density of liquid equals density of object. Density of liquid equals density of object. Right. Next one. Question 4. Question 4. Final question. An object floats. An object floats. An object floats. An object floats. In two liquids as shown. In two liquids as shown. As it's half immersed in each. 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 If densities of liquids are, if densities of liquids are rho and 2 rho. If densities of liquids are rho and 2 rho. If densities of liquids are rho and 2 rho, determine density of object. Determine density of object. Determine density of object. Okay, take this down. Take down the diagram and try the question. I'll start this in 3 minutes. This diagram, question 4. If you got any answers, put your answers to chat box. Online students. If you got any answers, put them to the chat box. Yeah. Any answers? Protect. Right. Right. Ask your questions if you have anything to know. Okay. Ask your questions if you have anything to know. You need any kind of clarifications? Please ask questions. Please do ask. Any other answers? Any other answers? Any other answers? Any other answers? Before I start, any other answers before I start? Good. 3 over 2. 3 over 2. Others? Any other answers? 1.5. Same no? 3 over 2. Right. Others? Please respond. Then only I know that you are on the track or not. Especially online students. Right? Online students, especially things you are joining online. Right? I don't have a visibility of you like physical students. Therefore, to make that connection, to bridge that gap, always you have to engage using the chat box at least. And I know whether you are on the track or not. And continuously looking at both chat boxes, please respond. And even if you didn't get something, just say that you didn't get it and explain again. And I know whether you are on the track or not. Otherwise, it's like blindly you are there. Please respond. No any other answers? I got only 2 answers. Both are 3 over 2. They said 3 over 2. Any other answers? No. Okay. Look at here. Again, if it floats in 2 liquids, right? If there are 2 liquids, 2 different upthrust acts from each liquid, right? So I mark these upthrust as, let's say the first one as U1 and the upthrust here as U2, U1 and U2. And weight of the object, mg, right? We are doing the same thing since it floats vertical equilibrium. Vertical equilibrium of object. Vertical upwards forces equal vertical downward forces. Vertical upwards U1 plus U2. U1 plus U2. Vertical downwards only mg. And we know thrust is v rho g. Thrust is v rho g. Right? Now, volume of the object is not given, right? But it says half immersed in each, right? So let's assume this immersed volume as V. If that is V, this is also V. If volume of the object is 2V, if volume of the object is 2V, right? I'm using V and V rather than using V with VO2 and VO2, right? Because then you get fractions, no? So therefore I'm using V and V. Then I'm going to consider the total volume of the object as 2V. Right? Total volume of the object has 2V, V and V immersed. Okay, U1 is due to the liquid rho. Right? Immersed volume in that particular liquid is V. Right? V rho G plus U2. U2 is due to the liquid here with density 2 rho. Immersed volume is same as V, but density of the liquid is 2 rho G equals mg. G cancels throughout. G cancels throughout. And here V rho plus 2V rho all together is 3V rho. 3V rho equals mg. Right? V rho plus 2V rho. 3V rho equals m. Now I need density. Density of the object. Right? Density of the object is inside mass of the object. Right? If you expand mass using density, then only you will include density of the object in the calculation, right? Density of the object is inside density of inside mass of object. Density of the object is inside this term mass of object. Expand it. So mass can be expanded as V rho. Mass can be expanded as V rho. 3V rho equals M is V rho. Then mass of object is volume of object into density of object. Volume of object, as I consider, it's not V, it's 2V. It's 2V. 2V and rho of the object, that is what is to be determined. I'll assume it as rho dash. Right? Okay, now V to V cancels. Same V comes, V to V cancels. V to V cancels. Right? Subject rho dash equals 3 rho. Rho dash equals 3 rho over 2. Right? 1.5, that's correct. 3 rho over 2. This is very much similar to the second or third question I did. Second. This is very much similar to the second question I did. Right? So make corrections if you have any. Make corrections quickly if you have any. Understood? And feel free to ask questions if you have anything to know. Finish? Finish? Okay. Next one. Question 5. Write down. Question 5. Write down the question. A hollow sphere. Question 5. A hollow sphere. Hollow. You know hollow sphere? A hollow sphere. A hollow sphere of density D, simple D. A hollow sphere of density simple D. A hollow sphere of density simple D of internal radius of internal radius simple r and external radius 2 simple r 2r and external radius 2 simple r freely floats in a liquid as shown. Freely floats in a liquid as shown. Freely floats in a liquid as shown. Determine density of liquid. 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 Take this down with the diagram given. And read the question carefully. This is a hollow sphere. Read the question carefully and just understand what's given and try it. We'll give you some time. Try it. This is given. Write out and put your answers. Check if you got any answers. Yes. Right? This is a hollow sphere. A hollow sphere. Any questions? Can you repeat the question from determine density? Determine the density of liquid. Determine the density of liquid. Any answers? Any answers you got? Any answers? What's a hollow sphere? No. Inside the sphere, that's a hole. That's a hole. That's empty, right? Inside this, that is empty. Internal radius is r. External radius is 2r, right? And mass is only distributed here, right? Substance is only here, and inside that's a hole. That's empty, right? So this is where the substance is distributed. The mass is distributed, right? Yes. It's not D. It's not D. I clearly said to you that if there are holes in the object, these one are going to be a solid object. In solid objects, if there is fully immersed in a liquid, then series are equal. That is right for any solid object. This is not a solid object. This is a hollow object. Hollow objects are like it's not D. My questions right? In the previous one, that was a solid sphere. This is a hollow sphere. Now there is different. Now there is different. I'm emphasizing again, this substance is or mass is distributed only here in this region. And in the middle, that's a hole. That's a hole. Hole means there's nothing, empty, right? Any other answers? The respective volume should be C only due to the distributed mass around that point. Double the hole. That respective volume should be something. Because mass is equal to rho. E is the volume where that substance is distributed. Right? As creates with that volume the substance. The actual substance is distributed. Except force, without force, except force. Uh, 8 over 7, 8D over 7. 8D over 7, that's a possible. 3 over 3 over 4D.
8DO7.
Okay, let's see. Any other answers before starting? Any other answers you got before starting? You said 3DO4. 3DO4. This is 8DO7. Any other answers? Any other answers? Now it seems. Let's start. Okay. So I'll mark the upthrust here as U and weight of the object as mg. Right? Same approach we have by considering vertical equilibrium. By considering vertical equilibrium. Vertically upwards forces equals vertically downwards forces. Vertically upwards we have only U. Vertically downwards mg. And U can be expanded as V rho G. Right? U is V rho G equals mg. Okay. Now V rho equals m. Right. Now tell me, what's the meaning of this V? Volume of the what is V as we defined, as we introduced? What is V as we introduced? No. This comes from upthrust. No? Left hand side is my upthrust. So this comes from upthrust. This V is immersed volume. That is immersed volume, right? Immersed volume of the object is, see, now this total volume is inside the liquid. No? Total volume is inside the liquid. This total volume of the sphere is inside the liquid, right? Which means immersed volume is going to be the external volume, right? Liquid doesn't know whether there's a hole inside or not, right? Just think of the perspective of the liquid. Inside the liquid, this sphere is immersed. Then what liquid knows is the external volume of this much of a sphere is inside the liquid, right? So immersed volume is going to be the external volume. Immersed volume is external volume. Right? Immersed volume is external volume. What's the external volume of this sphere? 4, 3, 5. External radius is 2r. Then it is going to be 2r cube. 2r whole thing cube. 2r whole thing cube. And what this rho is? Object or liquid? Left hand side. Object or liquid? This breaks down from upthrust. Right? If the ray is coming from upthrust, this rho is the density of liquid. Density of liquid. What did I ask? Object or liquid? Which density I asked? Liquid. Okay. Then rho is asked. And this is given as D. Right? So rho is what we are going to determine. Now, since density of the object is given, now we can expand this. So we know M equals V. M equals V. Now tell me, if I'm expanding this mass, this is the mass of the object. Right? Then respective volume should be the volume of the object. Volume of the object. Right? With the in left hand side, I have the liquid, upthrust and the liquid. In the right hand side, mg comes from object. Those are the terms related to object. Right? So this is mass of the object and volume of the object times density of the object. Right? And when it comes to volume of the object, right? Always volume should be considered as the actual volume. Actual volume in the sense, actual volume where the substance is distributed. Because mass is created only due to substance. If there is no substance, no mass. Right? Now, if there is a hole inside this, there's a hole inside this, and substance is only around it. Substance is basically plastic, you know. This plastic material is only around this tube. And inside, you know, that's a hole. Right? So therefore, that mass of the pen, let's say there is no ink or there's nothing inside the pen. We have just the filled like this, and inside there's a hole, right? And that particular mass is coming from the volume of the plastic. Volume of plastic. And they are medium typically mass, right? So mass of the object is always coming from, it's created from the actual distribution of substance. Right? If there's no substance, there's no mass there. Right? So mass always coming from the actual distribution of substance. Mass is always coming from the actual distribution of substance. Actual distribution of substance here is in this area only, this region. In this region. Because inside that's a hole. Right? Then V should be the actual volume of this mass distribution. Volume distribution of substance distribution. Right? Then this empty area should be substrate. Simply the hole should be substrate. It can be written as 4, 3, 5. The external volume of the cube is 2R cube, and the internal volume of the hole is R cube. Right? And this gives the volume of this part. Right? External volume is 4, 3, 5, 2R cube. And if I subtract the hole here, right? Volume of the hole is 4, 3, 5 R cube. And density into density of the object is D. Right? So this is the most important part here in this question, because this is a hollow sphere. Right? This is the most important part here. That's a hollow sphere. Right? Immersed volume is external volume, but the actual volume is the external volume. Actual volume is not the external volume. Always an actual volume is always it should be without holes. Actual volume is always without holes. Simple as that. Right? Actual volume of the substance is without holes. Hole like substance taking mass action. Right? Okay, that's it. Now, if you have written this thing properly, then here after this, there's a matter of thing. Invite. 4, 3, 5, 2. 4, 3, 5 answers. Right? 2R cube means 2 to the power 3 or 2 cube is 8. This is 8 simple R cube. And here, inside the bracket, 8 simple R cube minus R cube. D. Right? 8 simple R cube rho equals 7 simple R cube D. Right? R cube cancels. We are determining rho. Rho equals 7D over 8. 7D over 8. I saw the correct answer. No, is it upside down? You good. Who was that? No. You are saying 8 over 7. Oh, you were saying 7 over 8. It should be 7D over 8. It should be 7D over 8. Should be 7D over 8. Make corrections. If you didn't get the answer, make corrections. And if you have any questions regarding what I have done here, please ask. It is the most important line in this simplification. This line is the most important line in this simplification. Substituting the correct volume of hollow sphere. Right? You are saying 8 over 7. That's opposite. Upside down. Can you explain again? Listen. Force equilibrium is same as the previous one. Force equilibrium is same as the previous one. Upthrust equals mg. Right? Upthrust equals mg. Force equilibrium is same as the previous one. Right? And upthrust is due to immersed volume. Right? Upthrust is due to immersed volume. This is immersed volume. Immersed volume, right? Immersed volume means what is inside the liquid, right? What's the volume inside the liquid? That is immersed volume. Now, this whole volume is inside the liquid. This whole volume is inside the liquid, right? So, which means immersed volume is the external volume, right? No liquid goes into the hole. Now, if the liquid goes into hole, the story is different, right? Liquid next day we will be doing such questions, right? Open hole right? Now no liquid goes into the hole. Then immersed volume is the external volume, right? So that is 435 external radius 2r cube, right? And in this side we have mass of the object, mass of the object, mass of the object. Then if mass of the object is expanded, it should be volume of the object times density of the object, right? Volume of the object should be the actual volume of hollow sphere without holes, because mass is created only due to substance. If there is no substance, no contribution for mass from such parts. There is no contribution for the mass of the object from this empty area. That is empty, right? That's the logic here. That's the logic here, right? මේ size එකම තියෙන මේ solid sphere එකක් ගත්තොත් mass එක අනිවාර්යෙන් different if you consider the same density, right? ඉතින් මේ මෙයාගෙන් mass එකට contribution එකක් නැහැ. එහෙනම් අන්න ඒකයි line වෙන්නේ. ඒක තමයි කරලා. Right? So actual distribution of substance is only in this region, and that can be easily obtained if you subtract the whole from the external volume, right? External volume is same as before, and volume of this sphere, volume of the spherical ball is over the pi r cube, right? Into density of object, and that product gives mass of the object, right? Always mass is created due to substance, right? If there is no substance, there is no contribution for mass. That's the logic, right? I hope it's clear. So if there are any other questions, please ask and clarify. Okay, good. Simply keep in mind as if there are holes, the actual volume is always except holes, without holes. Actual volume of an object is always except holes. Seven DO8. Understood? This is just the start only. So we will go to much depth. This is just the start. This is like an average question, right? Or below average. Average, this is below average, right? Really getting good questions with good thinking parts, new thinking parts, good thinking. The following day, next day, right? This is average. So we are moving from simple questions to advanced questions. This is below average, right? This is just the start of hollow spheres and hollow objects. Spheres with a you can get any hollow object. Some other thinkings are also coming out, right? Okay. Write this down in red below the question. Write this down in red below the question. Write down in red. Mass of the object. Mass of the object. Mass of the object creates mass of the object creates mass of object creates with the actual distribution, with the actual distribution, with the actual distribution of, with the actual distribution of substance, with the actual distribution of substance. To the same point, therefore, actual volume of object should be considered. Actual volume of object should be considered. Therefore, actual volume of object should be considered. Actual volume of object should be considered without holes. Without holes. Without holes. Next point. What immersed volume in the liquid is, 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 external volume of sphere. What immersed volume of the liquid is, external volume of sphere. Right? That's the external volume of sphere. Right? Any questions regarding this? Any other questions regarding this? Right? Any other questions regarding this? All good? Online students? Online students? Any other questions regarding this? Yeah. Yeah. Okay. Right. So today we started Archimedes principle and law of flotation. And when it comes to questions, both contributes together. Right? You can see both contributes together. Actually, these are law of flotation. These are from law of flotation. Right? But when there are multiple of thrust, right? That is actually a deviation from law of flotation, because law of flotation is only for a single liquid. But there is an extra mile of law of flotation, extra step, next step of law of flotation. So always when it comes to questions, there will be a mix of Archimedes principle and law of flotation, right? So that's why I always encourage you to write vertical equilibrium rather than writing U equals mg from law of flotation. Because U equals mg is valid if and only if the object naturally floats inside the liquid, a single object. Right? If I keep another object on this, then again the direct application of law of flotation can be used. Likewise, the force frame, with the force frame given, with the forces acting, it changes. Force frame changes. Therefore, vertical equilibrium is common for anything. So always practice to vertical equilibrium. Then you can do any question without any hassle. Right? So flotation is just the starting point of the thinking. Right? But vertical equilibrium covers everything. Right? And next day we'll be moving towards all advanced questions. We'll be moving towards all advanced questions in hydrostatics. Not hydrostatics, Archimedes principle. Right? So this is just below the average questions we discussed today. Right? There are more coming up. You didn't see the real depth, the actual depth of this jet. Right? This, unlike the O-level Archimedes principle, so we are going to consider depth. Right? Thinking parts are there. Right? Now, if you understood Archimedes principle from the beginning of today, right? For sure, you will tackle other questions. You grab these things properly from the beginning. Right? Otherwise, there are no like such links with the previous hydrostatics part we did. We proved it using astrology and all that. But now, for Archimedes principle, no such connection with the previous parts. Right? And as I told you, within the month, we'll first 2 days we'll cover Archimedes principle, and then the rest we'll cover fluid dynamics. Fluid dynamics or equal hydrodynamics. Right? And with that, the entire mechanics will be finished. Right? And next month we'll be starting oscillations and waves. Right? And one spot exam is also coming now. Yes. One spot exam is also coming up from circular motion. And that's what we did from circular motion. And I wrote the paper now for 2 or 3 days in the class, but I didn't get any time to share the paper. Right? So let's see. Right? And the next day, since that's a holiday, I'll give you a holiday. Right? I'll give you a holiday, so don't come to the class. 10th Thursday is a holiday. Right? 10th Thursday is a holiday. 10th Thursday. Holiday. So it's a holiday. So we'll do the rest on the week after 10th, 17th. And when you are on the class after 2 weeks, then these things can be like Greek. Go through everything and come to the class, because I won't be explaining again from the beginning, because today we have start from this scratch and done everything. So come to the class with the reference of all these things, because we'll be moving this point onwards. Right? Any other questions? Anything to know? Anything to know? Online students? No. Okay. Now for online students, if you really need to drop me a private message, you can select host and do that. Otherwise, it seems you are reluctant to put these responses to the main chat. Right? I have noticed it. Right? So if you really need to put a direct message, select host and drop the message. Then only I will see it. Right? Okay, now questions? Okay, we'll wind up the session here. So let's meet on the next day. Right? Go safe, stay safe, and bye. Okay. Right. Goodbye.